I am in fact going to do something that is impossible for the next 45 minutes, which is try to describe software architecture by example in just 45 minutes. The least amount of time Mark and I do this on a regular basis is about 4 hours, so let's see if I can do it in 45 minutes. This, of course, the way I'm doing this is only talking about a sliver of software architecture, but it's an important part because it shows you why you really need software architecture, even if you have people from the design world or somewhere like that telling you, you don't need software architecture, you can just emerge stuff. We'll see why that's not quite true for complex problems. So what we're going to focus on today, in the brief time we have, is structural design in software architecture. And that really requires two activities to take place. I'm going to show you those by example with a simple problem: understanding the architectural characteristics or the capabilities we need to support for this system. And the other thing you need to understand is the domain that we're trying to build a software system for. We have a motivation for writing a piece of software. That's going to be part of the behavior of the system, and we have to model that as well. We have to do these two activities as architects. You can do these either in this order or another order or in more or less in parallel, but there's a really important join point between these, where these two activities come together, and that's what I'm going to illustrate today. And these two activities together give you enough information to choose the appropriate architecture style to start building your application. We're talking about a system that does not exist yet, a blank canvas, and so you're going to take the problem statement and figure out how to organize it in such a way that you can then go and build some software. So let's look at what that entails from a structural design standpoint. This is an example of an architecture kata. Mark and I, many years ago, when we started teaching software architecture, wanted a way to make it hands-on, because you can talk about abstract trade-offs all day, but it's not interesting. You have to tie it to something concrete to do real trade-offs against. And we fell upon this idea from another presenter. He gave us permission to use this idea of an architecture kata. These are small time-boxed exercises that stress some interesting architectural concerns. And that's what I'm going to use today, is this kata called Going, Going, Gone. This is an auction company that wants to take their auctions online in addition to their live auction. So this is not like an eBay. This is a live auction with an auctioneer with an online component as well, where online people can participate. We're expecting hundreds of participants per auction and potentially thousands of participants because we're running simultaneous auctions. Bidders can see a live video stream of the auction and bids as they occur. Auctions must be as real time as possible. Both online and live bids must be received in the order in which they're placed. Bidders register with a credit card, and we charge that if they win. And participants must be tracked via a reputation index. These are the kind of requirements we often get as architects from the business. Okay, here's my aspirations as a business. This is the system we want to build. We also include this extra context, which are not strictly requirements, but things that may influence your design. They're expanding aggressively by merging with smaller competitors. If the nationwide auction is a success, we're going to replicate the model overseas. We're not budget constrained because this is strategic. Some of these katas have budget constraints. And the company just exited a lawsuit where they settled a suit alleging fraud. So let's talk about what you would do as an architect here. This is all a very thin slice through our Fundamentals of Software Architecture book. And one of the things that we observed in this book is that pretty much the defining characteristic of software architecture is that everything is a trade-off. In fact, one of the ways to define software architecture decisions are decisions where there are significant trade-offs associated with each possibility. That's a software architecture decision. So let's look at first the architecture characteristics part of this. Some of you know this as non-functional requirements, which is hilarious because that term is left over from the ancient practice of function point analysis, which no one has done for real in about 30 years because it didn't work, but we still have this term. They're also called system quality attributes and cross-cutting requirements. We call them architecture characteristics. We just wrote the Head First Software Architecture book, and we call them sometimes capabilities, because these really define the things your system is capable of. And so You have a problem and you've decided, I'm going to write some software to solve this problem. You have a domain or problem domain. This is not to suggest that you should use domain-driven design, although there's nothing wrong with it. It's great, but there are other techniques as well. But I'm going to use the term generically, you have a problem, and this is obviously going to motivate how you design and build your software architecture. But you also have to worry about all this other stuff. And this other stuff are these architecture characteristics: reliability, availability, performance, elasticity, deployability, modularity, security, all the illities of software architecture. Yet another name for these things. This is what we have to analyze, the capabilities of the system. Because both us and business analysts are going to analyze the behaviors of the system for the domain, but mostly the architects are thinking about all these illities and these capabilities of the system. We looked, when we wrote our book, for a good definition of architecture characteristics and couldn't find one because they were either crazily out of date or really weirdly specific, and so we created our own. It's in 3 parts. The first part, architecture characteristics specify a non-domain design consideration. So this is that split I showed you at the beginning. Structural design in software architecture can be thought of as characteristics analysis and domain analysis, and the union of those two things is structural design in software architecture. The second part is it influences some structural aspect of the design. We're not trying to analyze the entire architecture here. What we're really looking for are things that really influence how we're going to choose an architecture style. Because one of the tricky things about these characteristics is that they are synergistic with each other and with your problem domain. In other words, if I want to improve security, I'm probably going to have a negative impact on performance because I need to do more on-the-fly encryption, more indirection for secrets hiding, and so I can't change one without affecting the others. They get all synergistically tangled up with each other. And so I have to be careful when you choose these things because the more you choose, the more they get tangled up. And so what we're looking for here are things that influence the structure of my architecture, because some problems can be solved with either design or architecture, but some things require architecture. Let me give you an example of that. Security is a great example of something that can be fixed with either design or architecture. If I'm building a monolithic system, I can build one part of the monolith with tighter security using encryption and salting and hashing and other good governance around that part of the information in that monolithic system. If I'm building a distributed system like microservices, I can build a service that has stronger authentication authorization and stricter access control around it and manage security that way. So security is one I can handle with either design or architecture. But some things can only be solved with architecture, like scalability. To a certain level, you can't really push a monolith beyond where you need a distributed architecture. Those are the things we're looking for here, are things that influence the kind of architecture that I'm going to need to support, what style I'm going to need to support this system. The other aspect of these things being synergistic is that you can't just choose them a la carte. This is not picking all of these that you want for this system, because if that were true, every system would be super performant and super scalable and super elastic and super secure and super all the things. Because if you could just do that, you would. But you can't, because these things often tangle up and counter one another. So what we're really looking for here are things that are going to influence the structural way we think about our architecture. And the last one of these is critical or important to application success. Because these things are synergistic, the more of them to support, the more complex your architecture needs to be. And so the goal as an architect is to support as few of these as you can get away with. One of the constant pieces of terrible advice you get in architecture all the time is to embrace simplicity as much as possible. And it's bad advice because it's just a goal but no way to get there. It's like saying you should lose weight. Well, okay, but you're not telling me how to do that. Well, here's one way to embrace simplicity: support fewer architecture characteristics. Because the more you support, the more complex your design has to be because they get all synergistically tied up with each other. One of the worst things you can do as an architect is over-engineer things because it gets really complicated really fast. You may be familiar with the ThoughtWorks Technology Radar, which we put out a couple of times a year. It's sort of our company's observation about the software development landscape. And one of the things that we called out a few radars ago, we call web scale envy. Because we kept running into these companies, like insurance companies, who are building these massively scalable applications, and we'd say, well, how many users are you supporting? And they're like, well, 50 or 60. And it's like, but you got so much complexity here. It's like, yeah, isn't it cool? And it's like, yeah, it's really cool, but wow, not great. So this is one way to achieve simplicity. Is to one path to simpler design is to support fewer things in your architecture. We also sort of overlaid this with explicit and implicit architecture characteristics. Explicit ones are, as it says on the label, things that are explicitly called for, like a certain performance or expected number of users, etc. But architects also make a lot of decisions based on implicit knowledge. Security is a great example of one of these. Even if it's not called out explicitly, you know you should not create an insecure system as you design it. But a lot of the internal quality characteristics in architecture also fall into this category, like modularity, because as an architect, if you design a system that barely limps its way to its release date and it can't be maintained and it's constantly failing and breaking, that's not successful, and so there's a certain level of internal design hygiene that also influences your decision process, but you're never going to get a story card that says, please don't screw up the modularity of the system as you build it. You just know that that's something that you should probably do. That domain design rests on top of these architecture characteristics, and we designed it like a pyramid on purpose because all of these things are kind of leaning and pushing against one another. In fact, one of the things that Mark and I like to say is that as architects, we're not really trying to achieve the best design, because best implies that everything is as good as it can be, and you can't because they're all fighting with each other. Instead, what you're always trying to achieve is the least worst design. What's the least worst combination of all these trade-offs that will work together? That's very often your goal in architecture, is to get to least worst. One of the families of these characteristics we care about a lot are these operational architecture characteristics, because these are the ones that often drive us from one architecture style to another, from a monolithic system to a distributed system, because once you hit a certain level of scalability or elasticity, it's very difficult to achieve that in monolithic kind of systems. And it's important to understand these capabilities before you start choosing an architecture style, because choosing the style first by saying, oh, we only do microservices is not smart, because you'll end up crazily over-engineering some things and not being suitable things for the other. It's the classic example of putting the cart before the horse. You people get busy working on the software, I'll go see what they want. It's not a good pattern for choosing an architecture. So when you look at a problem like going, gone, what you do as an architect is translate these business terms into architecture characteristics that they're talking about that you need to be able to support. So things like online auctions as real time as possible, yield things like availability and reliability and performance, things like nationwide scale and scale up to hundreds, and moving aggressively with smaller companies. Sometimes you get lucky and they use more or less your language instead of their language. You don't have to translate. We're obviously talking about scalability here. But some knowledge of the problem domain helps too, because think about auctions. What happens toward the end of auctions? People get excited. More people show up at the end, particularly if it's a valuable thing, and there's a ramp up of both the rate of bids and the number of people who are bidding. That's not just scalability, that's also elasticity. So I need to be able to support a certain concurrent number of users, but I need to handle that burst toward the end as well, when a lot of people show up to snipe at the very end of my auction. What about this one? Participants must be tracked via reputation index. This one is a tad mysterious as an architect. So what I would do is go find a subject matter expert, a business analyst, or someone who knows about this and say, well, okay, what is this thing? And they would say, okay, well, we don't want trolls to show up at our auction. We don't want people showing up and bidding and then disappearing without paying or annoying other people without bidding. And so it's a reputation index. We want to be able to, social grading to see who's nice and who's not, et cetera. Okay, that makes sense. So what kind of architecture characteristic is this? Well, it turns out it's not. You may go to something like, auditability or observability, but that's the way you might implement this. This is not an architecture characteristic. This is part of the problem domain. And there was a dead giveaway there. I said I had to go talk to a business analyst or subject matter expert. Elasticity, I know what that is. From an architecture standpoint, that means the ability to support a large burst of new users. But reputation index is something they made up. So I got to go find out what is this reputation index thing. So now I see what it is. Now my question is, do I need special architectural support for this reputation index thing? It's going to be something like a rules engine or a table or some sort of tracking, but I don't need special architecture to be able to support that, and so now I don't have to think about this at the characteristics level. I'll implement this when we do domain design, but that's not what I'm doing now. I'm trying to figure out what capabilities this system needs to support, and this one has nothing to do with those capabilities, so I don't have to think about that. Credit card, finances, of course, is security, but I put that in parentheses because, again, I can solve that with either design or architecture, so this is not driving me from one architecture style to another one. This is also tricky. Online and live bids must be received in the order in which they're placed, and we'll call this concurrency. The ability to resolve this thing, because we're going to have bids coming in live and in online, and we need to be able to resolve those things to make sure and make sure those things meet up. So we'll call that capability concurrency. So that's a good list of architecture characteristics that I would define for my going, gone system. The reason you need these for that architecture style analysis is that the architecture styles, the generic architecture styles that exist, pretty much any domain can be solved with any architecture style. There are really not that many differences in the way you implement a particular domain in one style versus the other. The styles really differentiate by the capabilities they support. How scalable are they? How elastic are they? How secure? How modular, etc.? And that's the thing that really differentiates the architecture styles. And so if feasibility, which is another important ility, is your number one driver, you're going to choose the simplest architecture style you can because you have to get to a finish line before a certain date because you are really limited on resources. This is the Twitter problem of let's build something and get it to market as quickly as we can because we don't have time to build the proper thing, and we'll build it later maybe if we're successful. If agility is your number one driver, you choose an architecture that's operationally a little more complex to get started with, but gives you really fast turnaround to be able to change things and update them very rapidly. If you want elasticity, there are specialized architectures like a space-based architecture that give you extreme levels of elasticity. Or if you want something like extreme scalability plus performance, you can use lower level architectures like event-driven architectures. But again, none of these really say anything about the domain that you're solving. Most of these are about the capabilities that you want to support. So that's the characteristics analysis, and we've done that for going, gone now. Now let's look at the other side of this analysis, which is the domain behavior. And this is much more contingent upon what flavor that you do within your organization of domain design. This is not strictly the realm of software architects, business analysts, and subject matter experts, and other people get involved in this as they should because they have the appropriate context for this. But what you're trying ultimately to do as an architect is get to components. Components are from components up are kind of the realm of software architecture, and from components down is sort of the realm of developers. And so as software architects designing a brand new system, what you want to do is create components that encapsulate the behavior that developers can then implement in a reasonable modular way. And we sort of go through this flowchart when we do this. We identify initial components. We look at the requirements that we have and see how well those match to these components. We assign roles and responsibilities to them. We analyze the architecture characteristics, and then we refactor. And notice this is an entire feedback loop right here of considering these things over and over again. So let's look at that process in terms of going. And we're going to use an approach called the actor-action model. But I'm going to show you a trap first. And so let's look at the initial components. One of the traps you definitely want to try to avoid here is something called the entity trap. It's really easy to fall into because you look at going, and you say, well, we have auctions, so we should have an auction manager to create auctions and browse auctions and schedule auctions. We have items, so we should have an item manager to create items and display items and upload images. And we have bids, so we should create a bid manager to place bids, display bids, and track bids. And so all this bidding stuff, or all this manager stuff going on here. And this is the trap called the entity trap. Because this is not an architecture, it's an entity relationship diagram. If this is actually what you need to just do CRUD operations on this, don't build an architecture, download a framework that'll just do this for you. There are a bunch of frameworks, you can just point to a database and it'll let you do CRUD operations on it and you're done. This is not an architecture. And this is a trap to fall into, and the way to find out if you're in this trap, the problem here is you're modeling entities, not workflows. So the first way to find out you're in this trap, ask yourself, when I use this system, are any of these things going to be tied up in transactions together? If the answer is yes, then you fall into the entity trap because you don't want to do transactions. If these were actually services in a service-based architecture, you don't want to do transactions across those things. You should be modeling workflows and not individual entities because we're not building an entity relationship. So let's use this approach called the actor-action approach. It was very closely aligned to sort of domain-driven design event storming, which is a way of identifying the actors in the system and the kinds of activities they're going to perform in that system. So we have here bidders, who are the ones who are bidding online for this auction. We have the auctioneer, who enters live bids, receives online bids, and gavels the thing sold. And then the system is often an actor in these situations. The system starts the auction, handles the payment, and then tracks bidder activity. So let's look at each one of these and build components for them, because we have a blank slate now. And so now let's start thinking about where responsibility would lie in this architecture. And so for each one of these activities, you ask yourself, should this be a new component, or could I use a component I've already created? Well, this one, I don't have any components, so definitely a new component here. Let's call it something like auction session. This is going to manage the life cycle of the auction for me. That's the thing that's going to start the auction. So let's look at track bidder activity. Do I already have a component that can handle that? Well, you could argue that auction session could handle that, but we would very quickly find out that every single thing here goes in auction session, and we've built a big giant God component, and that's not what we want to do. So you're actually better off going finer grained here and then consolidating than to start consolidating too early in this process. So tracking bidders seem like something that could be separate. But it's reliant on information because it has to know which auction that I'm tracking, and so track bidder activity needs to know some information from auction session. So now we're seeing dependencies starting to show up between our prototype components here. View live video stream. The existing component or brand new one? Well, none of these have anything to do with video or anything like that, so definitely probably a new component here for video streaming. What about live bid stream? Well, conceptually, those are similar, but very different information streams. One is video, and the other is just a data stream of bids. And so let's keep those separate. We may eventually consolidate those, but they are very different kinds of information feeds, so it's probably safest to keep those separate for now. Place a bid. Okay, we don't have anything yet that can allow us to place a bid, so we're definitely going to need a bid capture component. Bid capture, of course, needs to be able to send information to the bid streamer so it can see the bids that come in, and it's also going to need to send stuff to the bid tracker who's tracking the bids that will be multiplexed in with the live bids that are happening here as well. So that's the bidder activities. What about the auctioneer? Enter live bids into the system. Here we finally see some reuse because bidders need to place bids in the system, so do auctioneers. So we can reuse that bid capture component because from a behavior standpoint, that's exactly, they both need to enter bids in the system, and we have a nice encapsulated bid capture component to handle that for us. The auctioneer also needs to receive online bids. That's also bid capture because that bid capture knows exactly what those bids are and can receive the online bids from a bid capture. So that's nice. I'm able to reuse that component. Mark item as sold. Whose responsibility is that? New component or existing one? Well, actually, that's part of the definition of auction session. Start it and stop it. Mark is sold, so the auctioneer will go to the auction session and say this thing is now sold. And what happens after the thing is sold? We make a payment. Is payment part of auction session? Well, payment deals with money and security, and so we probably don't want to put that in the state machine for the auction itself. And so let's put a separate component for that. There's auto payment. And there's my prototype for a set of components that represent my going, gone world. This is very much like the output from some sort of design exercise like event storming or something like that. Here's why that's not sufficient by itself. Remember I said early on that you do these two kinds of analysis, architecture characteristics analysis and domain analysis. We've done both of those now, but I also said there's a join point. And now we've reached the join point between these two things, and it's right here. Once we've analyzed the roles and responsibilities and allocated responsibilities to components, now we need to come back and look at our characteristics perspective on these prototype components that we have. This is why you have to have done the characteristics analysis before you can continue to the next step. So these could be done in parallel up to this point, but this is the join point where now I need to apply what I've learned from that characteristics analysis to my problem domain here. And what have I learned? How many bidders do I have in this system? Hundreds per auction, maybe thousands overall. So bid capture for bidder has to be really scalable. I got to support at least hundreds per auction and across multiple auctions. How many auctioneers do I have per auction? One. I don't need scalability at all. For one, I have one auctioneer per auction. Huge mismatch between bidders and auctioneers. Let's talk about reliability. If one of my hundreds of bidders is in the middle of placing a bid and their connection drops and they have to reconnect and log back on and get back in line, they're annoyed. What happens if the auctioneer drops in the middle of the auction? No more auction. Company doesn't make money anymore. Company very, very unhappy about that circumstance. Doesn't like that circumstance at all. Would rather avoid that circumstance if at all possible. The point of this is that from a domain standpoint, bid capture is one kind of thing because I need to be able to capture bids. But from a capability standpoint, it has to be separate. I need auctioneer capture and I need online bid capture and a little bit more complexity because even though they support the same domain behavior, they have to support different capabilities. I really need scalability and high reliability for the auctioneer and different kinds of characteristics for my bidders. This is why those characteristics become important, because you eventually have to overlay how do the capabilities I need to support for this thing to be successful over on top of the behavior in the domain of your system. This is how those things merge together and line up. Now, you'll notice that, I'll go back one, when Mark and I tend to do this, we tend to use very lo-fi artifacts, because there's something I wrote about many years ago that I call irrational artifact attachment. There's a proportion to how long it took you to build something to how irrationally attached you are to that thing. If it took you 5 minutes to build something, you'll throw it away in a second. If it took you 2 days, there's no way I'm changing that. So the more formal the thing you create early on, the more attached you are to the thing for the thing and not the idea it has, which is why we use very lo-fi prototyping and sticky notes, because these are not precious at all. You can tear them up. But once we've solidified our design and convert those into actual components, these are going to be components in my system and the relationships between bidder and auctioneer and the dependencies between them. And now I can take these, give them to developers and tech leads, and now they can say, okay, for auction session, what do the code need to do within auction session to manage that auction session and create database relationships and those sorts of things. So that's the combined structural work of the software architecture. And now I have enough information together to choose the appropriate architecture style as a starting point. Now, we always talk about these architecture styles in this sort of pure, pristine, abstract state. But no software system is a pure anything. It's always some sort of hybrid. But what you're looking for here is a good starting point to build your unique system for whatever it is. And you're looking for the thing that's most closely aligned with the kind of capabilities you want to be able to support. The styles, these name styles, are ways to support different kinds, different sets of architecture characteristics. Mark and I differentiate these architecture styles from patterns. Styles are named topologies in software architecture, and that name implies both a structure of how components fit together, both logically and operationally, also how communication works within that architecture, the perspective that architecture has on data, whether it's unified or distributed, etc. So that style includes a lot of stuff, but each of those styles, because they delineate topology and communication, etc., have sort of certain capabilities cooked in because of the way that they do that. So one of the ways that Mark and I analyze these architecture characteristics, this is from our Fundamentals of Software Architecture book, and this is the part that I'm seriously cutting down from the longer version of this talk, where we spend much more time talking about the individual characteristics and how this chart was derived. This is very much like the cooking show, where they take the raw ingredients and put them in the oven and then pull the complete cake out. So here's the complete cake. But what this allows us to do is something that Mark and I refer to as qualitative analysis in software architecture. We talked about that a little bit this morning in the keynote, because, in the perfect world, given no constraints, what I would do is say, okay, boss, you've asked me to build the new accounting system for you. I'm going to build the new accounting system, and it will be the most perfect accounting system that we can possibly build. That's the good news. The bad news is it's going to take me 6 times longer and 6 times as much money as you currently have allocated for it, because we're going to build it in all 6 styles and then measure and see which one's best. You're never going to get a chance to do that. And so you need some way to filter these down based on their capabilities so that you can make reasonable judgments about them before you get to that point. One of the things that we can observe right away about gone is that bid capture and auctioneer bid capture have very different sets of architecture characteristics. They need different levels of scalability and reliability, which means we're in a distributed architecture. This is one of the guidelines that tells you, can I safely use a monolithic architecture, which is all of them share the same set of architecture characteristics? If some parts of my system need to support different capabilities than other parts, I'm probably in a distributed architecture, and so that knocks out automatically the layered monolith and microkernel, both of which are monolithic architectures. And I'll also mark out the service-based architecture because it uses a single database, and we need variable scalability here, which is harder to achieve in a single database like that. Which leaves me with things like microservices, event-driven architectures, or space-based architectures. And I can now look at the characteristics between these. So microservices and event-driven architectures are actually very similar, and in fact, events are used as a communication pattern in microservices very often. The big difference, though, from our perspective right here, event-driven architectures predate microservices by a few decades, and in event-driven architectures, we still typically used a single relational database or a few relational databases and did not have this bounded context idea that microservices have from domain-driven design, which was the inspiration for microservices. And so in choosing between those, we might say, well, how important is data isolation in this architecture? Should I use a single database or should I use more isolated data, which gives me ancillary benefits like ability to move faster because things are more decoupled and some things like that. The other alternative that we might think about is a space-based architecture, which is a very fancy thing with a lot of moving parts. It gives you really extreme elasticity, but that's not really the problem I'm trying to solve here. Bids are very much come and go because all I really care is the most recent one. I'm not trying to cache huge numbers of bids in memory because once your bid has been supplanted, it's gone. And so that's not really the problem I'm trying to solve. And so what you often end up doing here, what I really want is the data isolation in microservices, but the responsiveness I get with event-driven architectures, and so this is a really common combination. Let's use the microservices style, but use events as a communication pattern within microservices to get better responsiveness. And that's exactly what we're going to do. We're going to take the components that we defined as part of our analysis for characteristics and domain and translate those into services with persistence. So we're using a microservices architecture here. We've translated each of these into services, some of which have data and some of which don't. This is part of the decision you make as you build microservice architectures. Notice we've shared and created a data domain here because it seems like this is similar enough information and I don't really need independent scale between these two, and so I can share a data domain for that one. In terms of event-driven architecture, I'm going to use messages and events between this part of the system, and in fact, use things like message queues to manage the online bid and auctioneer capture. If I use an ordered message queue for that, then that handles the concurrency problem that I have as one of my requirements, because as those things come in, the queue is going to order them exactly in the order that they come in, and so as they arrive, I will let that handle the concurrency and be the join point for my two information streams for bids that are coming in. And so having an architectural element like this that solves one of my behavioral problems is a nice little bonus in this architecture. One of the side effects of using events and message queues as part of this overall design. So I did it. We did an architecture by example in just 45 minutes. This really shows why that characteristics analysis is important. And one of the things that I end up doing on a lot of projects that have never done that is go back and do it even with existing projects, because understanding those capabilities gives you a much clearer view of what trade-offs do I have and what things am I trying to make do too much that would really benefit from splitting because they have different capabilities. Even though they have the same kind of design behavior, you actually end up building a much simpler and much more suitable architecture for solving those kind of problems. And so to summarize here, everything in software architecture is a trade-off, and you have to keep doing this trade-off analysis over and over again, because every situation supplies different values for those variables. You can't just say, let's do microservices every time, because sometimes it'll work, but sometimes it'll be crazily over-engineered and more than you need. There are no right or wrong answers in architecture. It's always about trade-offs. And the second law of software architecture is that why is a lot more important than how. We derived these two laws as we were writing the fundamentals book. We were looking for things that seemed universally true. We were hoping there'd be like 10 of them, and there were 2 of them. Everything is a trade-off, and why is a lot more important than how. But every architecture decision needs to be accompanied by both technical and business justification, because the technical justification is fun, but you can spin off into all kinds of places if you don't anchor it back to what the business actually needs, because that's the real constraint that you have to meet when you design an architecture like this. The business needs and characteristics, the capabilities are really what drives that architecture. Thank you very much. Hope you enjoyed it.